So we are having another video, and this is reaction of benzene or arenes, and we are following A2 chemistry, and all my lectures are according to Cambridge textbook. Benzene undergo addition reactions, but harsh conditions are required. As in a previous video of benzene, I told you, like when benzene structures was like formulated, and there are 3 double bonds, just like alkene having double bonds. So it was believed like benzene will react just like alkene, and alkene easily oxidize by using strong oxidizing agent potassium permanganate in acidic conditions. In acid, it is easily oxidized. It produces ethylene glycol and gives some other products like aldehyde ketones that further oxidize into carboxylic acids. But when we treated this benzene with this KMnO4 like strong oxidizing agent, but benzene was stable. It didn't show any reaction. So this situation was surprising for us. And later on, we found benzene favors substitution reactions instead of addition reactions. It gives addition reactions, but we require some harsh conditions for reacting of benzene for addition reactions. So this is the substitution reactions of benzene. Like also we call them aromatic electrophilic substitution reactions. So actually benzene having pi electrons, pi bonds, and because of these pi bonds, electron density of benzene is higher. So benzene will act as a nucleophile, and for reaction of benzene we need some electrophile. Benzene readily undergoes substitution reactions. Benzene is a stable molecule due to resonance because its pi bonds or pi orbitals, they resonate, they change their positions because of resonance. They are delocalized orbitals. So when they change their positions, for example just like this is the one structure of benzene, and its bond are delocalizing, like this bond will shift here, this bond will shift here, and this bond will shift here. So these are delocalized pi bonds. Because of this resonance, benzene molecule is stable molecule. A strong electrophile is required for a reaction with benzene. As we know, benzene is stable due to resonance, so we have to produce some strong electrophile to attack over this benzene pi electron system. The first thing is reaction with bromine and chlorine. So when we try to react benzene with this bromine molecule, Br2 molecule, in the presence of some catalyst, and we use like FeBr3 iron bromide, FeBr3 catalyst, and we get bromobenzene. The actual thing is mechanism of this reaction and how this reaction proceeds. Actually what happened, we know bromine is a non-polar molecule. It's not a polar molecule. How a bromine converted into a strong electrophile? So mechanism of this reaction is Actually, when this bromine molecule, this is the bond of bromine Br2, and these are the electron of this bromine, and this is the electron of this bromine, and we are reacting this with FeBr3. AlCl3, FeBr3, FeCl3, okay, they are known as halogen carriers. Actually, what happened, this lone pair of electrons, when both they come close to each other, this pair of electron actually attracted towards this iron, because this iron, in this iron, 3d orbital having a space. So these two electrons, they are attracted towards this iron orbital. So when this molecule come close to this FeBr, so it feels partial negative, and this electron of this bromine also attracted towards this. That is why this bromine feels partial positive. Okay, so this lone pair of pair of electron makes a dative bond or coordinate covalent bond, in which one lone pair from one molecule attracted towards the electron deficient atom. Now 3d orbital of this iron accommodate these two electrons, and it makes bromine positive, which is our required strong electrophile, and we get FeBr4, Fe 1, 2, 3 and 4, and we get this FeBr4 having negative charge on iron as a whole molecule. Okay, so this is our required strong electrophile. Now what happened when this benzene molecule actually comes close to this Br positive, which is our strong electrophile. We need this strong electrophile because benzene is stabilized. So this bromine positive attached to this pi electron system of benzene, and this is the movement of electrons, like pi electrons are being attracted to this bromine positive. And in our first step, we get like this bromine on this carbon, and this is the hydrogen of the benzene, because each carbon of this benzene having one hydrogen, as we discuss in structure of benzene. So what happens, like when this bond breaks, our positive structure, like positive charge. So let me explain this phenomena, like why this positive charge and this curve is produced and what is the representation of this. Actually, when bromine like this, when this pi electron system intact with combined with this bromine, so this bond broken down. Okay, so we get this bromine will combine here, and now this is the hydrogen of this carbon. At this carbon, this is the hydrogen. So at this carbon we will get a positive charge, because this carbon is making three bonds, one bond with this hydrogen, one bond with this carbon, and one bond with this carbon. But this carbon still making four bonds, 1, 2, 3 and 4. All other carbons are sp2, as we have discussed in structure of benzene. But at this stage, at this ion form, this carbon having sp3 hybridization, because it's making four bonds, 1, 2, 3 and this 4. So this positive charge, actually this electron will shift here, then positive charge will shift here, then this electron will move here, then positive. So representation of this structure is made by this structure. It means like positive charges rotating around this, like electrons are rotating. Okay, so what happened in the next step? Next step is the second step, is where we are using this negative FeBr negative, FeBr4, and overall charge is negative. So actually this electron extract this hydrogen, and electron of this hydrogen, they turn back, they make their bond again. So we will get this like this, our benzene, and here we will have our bromine molecule. So this is bromobenzene. So we will get this like hydrogen and one of the Br here. So it will get, we will get HBr plus FeBr3, again our catalyst, FeBr3. So very same thing what happened there, like this is actually representation of this charge. So this carbon having positive charge, then the electron move here, then the positive charge shifted here, then these electron try to fill this positive charge. Okay, so there is like rotation of these charges. So this is the representation of this. So at this point this carbon making sp3 hybridization, okay, because connecting making 4 bonds, 1, 2, 3 and 4. So this ion is known as arenium ion. This ion is known as arenium ion. Okay, so this is like mechanism of bromine in the presence of FeBr3, and here our products, further products are like HBr plus we are having FeBr3 again, our catalyst. So this is the reaction of bromine with benzene with its complete mechanism. So our next reaction is like reaction with chlorine. Just like this, we are having this benzene reaction with Cl2 in the presence of AlCl3, and we will get this product, chlorobenzene. Okay, just like others, like remaining we will get some HCl and AlCl3 again as our catalyst. So what is the possible mechanism of this reaction? Like the mechanism is just like the same as we have discussed before. For example, we are having this chlorine and electron of this chlorine, and this is electron of this chlorine, and they both will make a dater bond with AlCl3. As we know, aluminum is deficient of electron. It has a room space to accommodate these electrons. So these two electrons will move here and they will make a dative bond. I am adding another concept like FeCl3, AlCl3, FeBr3. They all are actually Lewis acids. Lewis acids. We will discuss in acid base. Mean Lewis acids are those they can accept pair of electron. So they are also Lewis acids, and they are also known as halogen carriers. Halogen carriers. So this lone pair is being attracted to this. It will have negative charge, and electron of this chlorine will also attract to this side. So it will have positive. So we will get our electrophile chlorine, and then again AlCl4 negative. aluminum tetrachloride with charge of negative. Okay, so this is our strong electrophile. Once again, we need strong electrophile because benzene is stable molecule. So we are reacting this benzene, and this is our Cl positive electrophile. So any one of the pi electron, either you can start from here, you can start from here, either you can start from here. This is your choice, no problem. For example, I am starting this from here. Like now this is like electrophile is being attracted to this pi electron system because this is negative and this one is positive. So when it will attack here, we will get because this bond carbon pi bond of this carbon and this carbon. Okay, so we can make the product either on this carbon, either at this carbon. Okay, so I am like drawing one hydrogen here. This is the hydrogen of benzene, and this is the chlorine which is act as a attach here as a electrophile. So these are the like remaining bonds of this. Either you can draw in simple in this way, but according to your IGCSE your pattern, you have to follow their pattern. So that is why I am erasing this, and I am erasing this. I am drawing like according to GCSE, IGCSE or A levels pattern, and we will get here like we will get here just like oh, it's not working, sorry. I don't know what is the problem with this. Okay, now like this one having some positive charge here, and rest of the thing here will be some like positive charge, and that represent the rotation of that charge within the molecule. So we will draw here some this and showing this positive charge. In the very same step, just like this AlCl4, like this AlCl4, AlCl4 is negative charge, like this will attract this hydrogen, and this electron of like hydrogen is removing without its electron, so it's moving back to its position, and we will get the product chlorobenzene. This is our product chlorobenzene, and this Al, then H, and this Cl, it will become HCl, and we will get our remaining catalyst AlCl3, aluminum trichloride, as our catalyst. So this is the mechanism of like bromine of the reaction. And so the next thing is about this reaction in your textbook. For example, we are having methylbenzene. Already methyl group is attached with this benzene, and now we are going to add Cl2 in the presence of catalyst AlCl3 or either FeCl3. So what happened? Actually, this group which is already available on the benzene ring is electron donating group. This methyl family, like or alkyl family, methyl, ethyl, propyl, butyl, they actually donate electrons to this ring. This is hyperconjugation phenomena, and I will inshallah discuss another video in detail what is hyperconjugation. So when this any group donates its electron to this ring, it actually activates this ring, and when the ring activated, we get our product like this is our Ca3. So we can get this Cl either at this position or either we can get this chlorine at this position. In next video, like orientation of benzene or like substitution orientation of benzene, I will explain all the internal mechanisms why the chlorine is attaching. This is carbon number 1, this is carbon number 2, this is carbon number 3, and this is carbon number 4. So we are getting 1 chlorotoluene and we are getting 1, 2, 3, 4 chlorotoluene. Okay, so why we are getting this on carbon number 2 and carbon number 4? In that lecture I will explain with all the logics and complete reasons. Okay, so if we are adding a lot of chlorine gas, for example we are having more chlorine gas, so we can get the product like just like this. We can get one of the product like this is our Ca3, one of the chlorine here and one of the chlorine here. So these like position number 2 and 6, position number 2, so 1, 3, 4, 5 and the carbon number 6. So position number 2 and 6 they are identical. Okay, position number 3 and 5 they are identical. Position number 1 and 4 they are identical. If we add further chlorine gas in bubble form, so we will have another product, like we will add chlorine, we will find chlorine here, here and here, 2, 4, 6. Actually why? Chlorine is just adding on this 2, 4 and 6. This is just because of this available group. Okay, for example we are having phenol here, we are having OH, so we will also get these products on 2, 4 and 6 position. Okay, if we are having aniline or amine benzene, for example NH2, these three groups 1, 2 OH and these are ring activating group. Actually they activate the ring and they make products either on carbon number 2, either on carbon number 4, either on carbon number 6. So these are the we will explain the reasons in like our separate video, like what is the reason behind this, why these molecules are combining at these positions. So another thing is, for example if we are having this methylbenzene, this is our methylbenzene, and now we are using this chlorine, but we are using sunlight, UV radiations. Okay, this is very important question. This is like side chain reaction, like we are reacting the molecule not with this ring. Okay, as we learned in alkane, like when alkane CH4, for example methane, when they react with chlorine in the presence of sunlight or UV radiations, it gives us a radical reaction or radical substitution reactions. There we get some radicals and hydrogen replaced with this chlorine, like we get this product like this hydrogen replaced with this chlorine and we get HCl. Okay, in second step, like second hydrogen replaced with chlorine, and one by one all hydrogens replaced, one by one all hydrogen replaced with chlorine, and we get this product. We discussed, we have studied this in alkane reactions, just like this here. If we are, for example, having our reaction methylbenzene with chlorine, but we are having a condition that is sunlight, so it will also give free radical reaction mechanism, but it will not react with this benzene molecule, it will just react with So it will just, this chlorine only will react with this methane, either you can say methyl. So it will, like this is benzene and this is CH3, so it will have one chlorine and two hydrogens, because one of the hydrogen of this replaced with this chlorine. If we add more like chlorine, so one by one all these hydrogens, for example we are having this hydrogen, chlorine and chlorine. In the next step, UV as the radiation is the condition, we will get this product. Like one by one all these hydrogens are being, chlorine, chlorine and chlorine. So it means like in the presence of this and that suitable AlCl3 FeCl catalyst, like benzene will not be affected, and these conditions produce a radical, and one by one all hydrogens will be replaced. Okay, so this is like chain radical reaction mechanism. Okay, the next thing is, next topic is about nitration of benzene. Nitration. So nitration means introduction of NO2 group. Either we are introducing NO2 group, this is the nitro group. NO2 group is known as nitro group. When we are introducing this group in benzene, so this is known as nitration. So we are having this HNO3, actually this is NO2, this is OH, this is nitric acid, actually HNO3 nitric acid, and we are reacting this nitric acid with a catalyst, that is our sulfuric acid H2SO4. So what will happen now, this H and OH, they will combine together and they will give us some water, H2O, plus we will get this NO2 group. Actually this is our required function group and this is our required electrophile. We will get this NO2 as our electrophile, and we will get our HSO4 negative, plus we will get this is our HSO4 negative. So we have got our desired like electrophile, that is strong electrophile. So we will react this electrophile with this benzene molecule. So this is pi electron system. So this NO2 will attach with this pi electron system. These curly arrows actually movement of electrons, like electrons are flowing from this to this side. Okay, so just like in other step, this is the first step. In the first step, what happened, we will get again like this positive charge that is like rotating here, and we will get this NO2, and at this carbon, this is the hydrogen, like each carbon of benzene having hydrogen. I even told you like now all these carbon are sp2, but this carbon is sp3 hybridized. Okay, so in next second step, this oxygen like HSO4 negative, like this O will combine with here, you have to write HSO4 here, HSO4 negative. So actually this negative like will extract this hydrogen, so electron of this hydrogen, it will go back and it will make a bond here. Once again, restoration of bond, so that bond will be restored and we will get this nitrobenzene, NO2 nitrobenzene, and we will get again over this H2SO4, that is our catalyst. Okay, so this is the nitrobenzene, and this is the mechanism of nitration of benzene in the presence of sulfuric acid. So our next reaction is sulfonation. In sulfonation, we are introducing sulfonyl group in benzene. This is SO3H. This group is known as sulfonyl. And when we are introducing this group in benzene, so this is called sulfonyl. For this, we are using sulfuric acids. Okay, of course they are not similar sulfuric acids, and we will get our one of the electrophile SO3. Okay, and we will get our HSO4 negative, just like our previous mechanism, and we will get H3O positive hydronium ion. So the important thing for us is this, because this will react with this benzene. Actually this is sulfur connected with 3 oxygens. Oxygen is more electronegative than this sulfur. So this and these oxygens are pulling the electrons of the sulfur towards itself. That is why making this sulfur more positive. So it will react here, and one of the pi bond like of this, one of the pi bond like electron of this electron, they will move here, okay, with this oxygen. Like you can move any one of them, okay, like there are 3 possible bonds. So in the first step, once again we will have this structure, and as usual we will make here some this positive charge, okay, that is like resonating, like that is moving here, and we will attach this sulfur and double bond with oxygen, with the oxygen negative charge, because one of the bond broken here, so it's oxygen negative. And just like other, we are having one hydrogen, just like previous of our mechanisms. So this is the hydrogen of benzene, because each carbon having one hydrogen, okay. So the next thing is we will have this HSO4 negative in next step, this HSO4 negative, just like previous nitration mechanism. So this negative will come react with, and this bond will shift back to its position, and we will get our product oxygen and single bond oxygen and bond restoration. And this hydronium, like for example we are having this hydronium ion, water gets its proton from the acid which is as a catalyst. So this oxygen will extract this hydrogen, and without its electron, so these both electron will move to this, we will get this water, and we will get our final product, that is sulfonyl benzene, sulfonic acid. Is it? So this is our product. We have successfully introduced this SO3H group in the benzene ring. So no, this is not a time of addition reactions. So in I think let me complete the next video of this. Okay, I will inshallah add some other video in next video. Okay, let me remove this, and I am explaining like the last mechanism of alkylation, acylation and Friedel, like Friedel, alkylation and acylation, alkylation and acylation. So first thing is we are introducing alkylation, like we are now adding alkyl group. For this we need some like Ca3 methyl, okay, chloromethyl like methyl chlorine or chloromethane, and reacting with this AlCl3, okay, because they are halogen carriers, and this electron of chlorine, this electron of this, they are making some dative bond or coordinate covalent bond with this, and we will get this Ca3 positive here. This is our electrophile, and we are getting this AlCl4 with negative charge. So this is our benzene. As usual, we are having our strong electrophile, okay, so this will react with this, okay, and in the first step we will get our ion, arenium ion. This thing is known as arenium ion. Arenium ion. This is our arenium ion. So here, either here on this is your choice, because according to me, like this bond being attacked here, okay, so either here you can draw. So I'm, for example, this is the hydrogen of that benzene, and this is the Ca3, okay, molecule being attacked here. So this AlCl4, just like in our previous lectures, AlCl4 negative, it will extract hydrogen from here, and this electron of it will make bond again at its position, so we will get this methylbenzene. We will get this methylbenzene. Its special name is toluene. Special name is toluene, either methylbenzene. So Friedel were two scientists. So this is alkylation, like we are introducing some alkyl group in the benzene, okay. So the next thing is acylation, introduction of acyl group in benzene. So next thing is acylation. Acylation, okay. Actually this group, like alkyl with this carbon double bond oxygen, this, if carbon is having positive charge, so this group is acyl group, and when we are gonna to like substitute hydrogen of benzene with this group, so this reaction is known as acylation. So we need to create this acyl. So this acyl chloride, a highly reactive derivative of carboxylic acids, okay, they are produced from carboxylic acid. They are a derivative of carboxylic acid. They are very reactive because this carbon is connected with this chlorine and oxygen. Chlorine and oxygen, they both are highly electronegative, and they are making this carbon more electrophilic. So the next thing is we are reacting acyl with AlCl3, AlCl3. So this electron of chlorine and this electron, so they are also making dative bond with this aluminum, just like the Lewis acid as our previous mechanisms. So we will get this electron of carbon also moving here. So it means we will get this R, carbon double bond oxygen, plus AlCl4, AlCl4 negative, okay. So this is our required strong electrophile. We are reacting benzene with acyl group, positive charges here, so it will attack on this carbon because this is electron deficient, and we will get our this positive charge and carbon double bond oxygen and our R group, and this is our hydrogen. As usual, this AlCl4 negative, AlCl4 negative, it will extract this hydrogen and it will turn towards original position. So we will get our final product, carbon double bond oxygen with this R. So if we look into this, like for example R, we are using methyl, so we are having this carbon double bond oxygen, CH3 or CH2, whatever the thing is, okay. So this is acetophenone, like this is our methyl group, and this is our like benzene ring, phenyl ring. So this is the carbon of benzene and this is the carbon. So this is a type of ketone. Its name is acetophenone. Okay, this is our product. So this is like a acyl group is being introduced in benzene. All in these reactions we are seeing like double bond is restored again. One of the hydrogen of this benzene is like going out, and instead of that hydrogen we are adding another group, atom or molecule. So this is substitution reactions. Okay, we are substituting, removing hydrogen or like bringing some other atom or molecule in the benzene. So like benzenes, all bonds are completed, just this position of hydrogens replaced with this molecule. So these are the like possible mechanisms of aromatic electrophilic substitution reactions. Next thing is addition reactions of benzene. As I told you, like benzene dislike addition reactions. Reason is, first the harsh conditions are required, and second is the lost aromatic character. For example, this is benzene, 3 double bonds, adding 3 molecules of hydrogen in the presence of nickel catalyst or like platinum or platinum. Okay, this is hydrogenation reactions, and we will get the product cyclohexane. The first thing is like this is difficult for benzene to proceed with this reaction. So if we successfully provide the conditions, and if we successfully like add these 3 molecules of hydrogen with 3 bonds, we will get this cyclohexane. Its chemical formula would be C6H12. Its chemical formula is C6H6. Okay, so this is no more a benzene. Either you can say this is no more aromatic compound. So if benzene proceed with addition reaction, so it lost its aromatic character, like a resonance phenomena. Okay, another reaction, for example, we are adding this like alternate double and single bond, 3 molecules of Cl2. If we are adding this not in substitution way, we are adding these molecules in addition ways. Okay, if we use FeCl3 or AlCl3, then they will substitute here. Hydrogen will replace with this chlorines. No, I am making addition product. So we will get this, all this double bond will broken down, and each carbon of this, like there are 6 chlorines, 3 2s are 6. So on each carbon we will get a chlorine. Okay, because double bond is broken down, because this is addition reaction. So this is not anymore like aromatic. This is simple like cyclohexane with 6 chlorines, and this is simple cyclohexanes. So these were the reactions of benzene. I just explain very short about addition reactions of benzene because they are not favorable with benzene. But the important point to memorization is harsh conditions required, and the benzene lost its aromatic character. Thank you very much. Allah Hafiz.